All right, everybody, this is Math 111, 9.2 notes, page 6. A SRS of size n is drawn. Simple random sample. The sample mean is to be found to be 35.1, and the sample standard deviation has already been pre-calculated to be 8.7. Construct a 90% confidence interval for this data set of sample size 40. First of all, 40 is greater than 30, so that we can assume that this is a normally distributed curve. After doing that, we want 90% of the data to be the middle 90%. That leaves 10% on either side. That means 5% could go here and 5% could go here. Filling in these for the upper and the lower bounds, we're mostly done. 35.1 plus or minus the t-value. That's what we're going to get right now. We got to look up the t-value that has 0.05%, 0.05 to the right of it. What's our degrees freedom? 39. So we go to row 39 and we're looking at 0.05. 39, I hope you guys can see this. 39.05, there it is. 1.685. So we insert 1.685 times the standard deviation, 8.7, divided by the square root of 40. Plug that into your calculator, and you get a lower bound of 32.78. 32.78. And then use the positive part of that, and the upper bound would be 37.42. Once you do enough of these, they're all the same. If you have any questions, just shoot me an email. This time we're going to construct a 90% confidence interval for a sample size that's a little bit larger. What do you think that's going to do to our upper and lower bounds? Again, same exact data we want. 90% in the middle. That means 5% is on the edges. And our lower bound, it's going to be the average, 35.1, minus the t-value that we're going to look up right now. We're going to look up the t-value, but this time we want to use a degrees freedom of 99. One less than the n value. So if you grab this table, and if you haven't watched any of the other videos, this table comes from page A-11, A-14 of our e-text. You can check it out in our e-text. I printed mine out just to make it easier, but I think when you get on Pearson, you'll have a link that will go straight to this. If you look down here, they don't have a degrees freedom of 99. So whenever that occurs, we just use the closest one to it. In this case, it's 100, okay? We want that 0.05 or 5% of the area to the right. This time we get 1.660. 1.660. The average, the standard deviation is still the same, but this time we take the square root of 100. That's the lower bound. To get the upper bound, just add that extra stuff. So the lower bound this case, 33.66, and the upper bound is 36.54. So what's happening is it's shrinking towards the mean. The more data values we have, the more confident that our values will live closer to the average. That's what happens to it. It shrinks. It becomes smaller. This time, construct a 98%. We want to be 98% sure that all the data values lives within that number of standard deviations. So again, the degrees of freedom is always one less than n. 39 is on our data table, so we will be able to look that up. The lower bound is 35.1, plus or minus the t-value that we need to look up into our chart. This time, 98% changes our normally distributed curve. We want 98% of it to be the middle. That leaves 2% to divide equally amongst both sides. That just leaves 1% on this side and 1% on that side. As a decimal, 1% is 0.01. So we're going to look up 0.01 with a degrees freedom of 39. 0.01 way down here with a degrees freedom of 39. Good Lord. Way down here. I hope you can see this, guys. I keep saying that. I got 2.426. 2.426. 2.426 times 8.7 over the square root of 40. And to find the upper bound, you just add that value in there. So the lower bound this time, 31.76, and 38.44 is the upper bound. Let's compare the upper and lower bounds to the very first problem that we did. If we want to be 98% certain that our data lives close to the mean, that means our data value is going to have to spread out a little bit. Does that make sense? I hope it would. Email me if you have any questions on these things, or pause the video and think about it for a minute. Last bullet point here, it says if the sample size of just n equals 18, what condition would we need to be to satisfy in order to compute a confidence interval like we've been doing? I love it when we get a problem like this. Remember, the number of data values has to be above 30. If it's not strictly above 30, we don't have to do this problem. Not enough data. We would need to know that the data is normally distributed, and if they wouldn't say the word normal or normally in a problem, then we wouldn't have to do it at all, okay? I hope this is helpful, guys. Shoot me an email if you have any questions. We'll talk to you soon.